I'm going to explain the third important article of Alex Graves and DeepMind Company. So it started from Turing machine, and then they implemented a differentiable neural computer, and now they want to scale it to have the sparse read and write. So this is this article in 2016 that I'm going to explain. But there are other articles as well related to this. So these are positive samples. Attention approximates sparse distributed memory. So the goal here is that here we represent an end-to-end differentiable memory access scheme, which we call sparse access memory, that retains the representational power of original approaches while training efficiently with very large memories. So it's a problem that what if your memory increases? So it becomes very sparse because you remember those WI, those weights that attend to different pieces of memory locations, different locations of the memory, and that was very sparse. Becomes very sparse if you increase these memory. If you have a very, very large, the size of this is very large, it becomes sparse because just like the problem of softmax in deep learning, if you have many neurons, then it becomes very sparse. For example, 0.23, this is the amount, the portion that is attending to special location. So it's very sparse. And otherwise, for many of them are just zero, almost zero. And so how can we deal with this problem? In my opinion, you just neglect, just omit those low numbers. If it is less than a threshold, then just omit it. And suddenly, after reading this article, I saw that this is exactly the same idea that I have. And so you know what is the idea. You're just ignoring the weights that are higher. So here, the sparse read operation is defined to be a weighted average over a selection of words in memory. For example, this W tilde here contains k number of non-zero entities, and k is a small constant, independent of n. So k is just 4 or 8. This k is just 4 or 8. We will refer to sparse analogues of weight vectors as W tilde, and when discussing operations that are used in both the sparse and dense versions of our model use W. We wish to construct W tilde such that R tilde as approximates RT. For content-based reads where omega R is defined by 2, an effective approach is to keep the k largest. So as I said, we just keep the k largest non-zero entries, set the remaining to 0. So we ignore those very low values. Just pick the best k values, the biggest k values. The same thing for write, because if read is sparse, is okay, just k values, then the same thing happens for write as well. And here I, this indicator function, is over words in the memory with value 1. If the word minimizes a usage measure, using some locations. And if there are several words that minimize U, then we choose arbitrarily between them. We use arbitrarily between them. And we tried two definitions of U of t. This definition of U of t is important. The first one is time discounted sum of right weights. And they use the controller efficient backpropagation through time. I want to explain this one, approximate nearest neighbors. So when querying the memory, we can use an approximate nearest neighbor index to search over the external memory for the k-nearest words. Where a linear k-nearest neighbor search inspects every element in memory, an ANN index maintains a structure over dataset to allow for fast inspection of nearby points in order of log n time, which is good. Sublinear. And in our case, the memory is still a dense tensor that the network directly operates on. However, the ANN is a structured view of its contents. Both the memory and ANN index are passed through the network and kept in sync during writes. So read is the same as previous lecture, but here is a sparse version of that. Just keep the K most important. And everything else is just the standard. You get derivative, you take the derivative with respect to those weights. And for write as well, they use, this is very similar because they use erase and add, very similar. So they use the backpropagation. So this is external memory, but all of these long short-term memory considered as an internal memory. We have an external memory as well. So we are generalizing LSTM here as well. So this is a sparse differentiable neural computer. That linkage is updated a different way than in previous lecture. The temporal linkage can be used to compute read weights following the temporal links, either forward or backward. This is forward, this is for backward.